are the blanks and the characters of the text. Smaller entropy means less symbols, obviously. And compression, what compression does is it increases entropy. To understand that, you have to think of compression as a mechanism that introduces more symbols which describe groups of other symbols that are the basis of the compression, the original data stream. If you're interested into or if you want to have more details, visit the pages. You can download the PDF of the file afterwards. Okay, first simple algorithm of compression is pattern matching. The mechanism is quite simple. If you have your input data stream saying Dr. Dobbs, Dr. Dobbs, Dr. Dobbs, you see that this D can be found in the input stream before, at position 0. So what you do is you do not store the actual character, but the distance to the previous character and the length of the match, as it is done here too. This is an interesting case, by the way. As you see, the match overlaps. It starts here, -8, starts here, and goes till position 9, which includes some of the characters of the match itself. How does that work? If you imagine how this is decompressed, you'll see that it works. You go back at 8 positions, you copy this character here, then this here, and so on. And if you are here, you will copy those balls you just copied in this match. Okay. It obviously doesn't make not so much sense to store matches with length 1. If you put every offset and length into a single byte, so you what you do is you encode the matches with so-called prefixes. So what you do actually is you don't store 8 bits for every single character here for a literal match, so-called literal match, but you prepend it with a 0. So if your decoder comes there, sees a 0, he knows the next 8 bits are a literal match, which is to be copied from the bit stream of the compressed data. If it sees a 1, it knows it's a match. Now it has to determine which match it is, whether a 1-byte match, which is denoted by a 0 here, or a longer match, which is denoted by a 1. And then it reads the following bits. For a 1-byte match, it only reads the offset, and for a longer match, offset and length. In this case, both 4 bits. And considering this encoding, you can see that the resulting data stream will be shorter than the original one. The original one has 168 bits. The encoded one is much shorter, 92 bits only. You have 6 literals to copy, 3 1-byte matches, and 2 longer matches, which makes up for 92 bits. This algorithm has extremely low memory requirements. You just need your data stream and have to look back into the data you already processed to determine the matches. Of course, there are a lot of optimizations which will require more memory, but we'll keep it simple here. The decompressor of pattern matching is quite small, as I already explained. You just have to look back the offset and have to copy some bytes. It's only a few lines to decompress such a thing. Of course, the encoding has to be reversed, but that usually isn't that complicated. The compression is slower than the decompression. You always have to look for matches. If you decompress, you already know the matches, so the decompression effort will be a linear one. You just have to go back and copy bytes, nothing more. Next compression algorithm is Huffman encoding. Huffman encoding is a very simple scheme. which does the following. It just counts the characters. In this case, we have 6 Ds, 4 Bs, 3 white spaces, 3 Rs, 3 Os, and 2 Ss. What you do then is you take the probability of the symbols or the frequencies, and of all symbols. We have obviously 21 symbols, and you divide them into equal groups, so that the frequency of the groups will be almost the same. Then you create a new code for these symbols by following the tree. If you go to the left, you put a 0. If you go to the right, you put a 1. This results in shorter codes for symbols that are more frequent in the file. As you can see here, the D only has 2 bits, the R has 3 bits, for example. And you see that Huffman encoding gives better compression usually than plain pattern matching without proper encoding. The encoded stream for this simple version of Huffman encoding has only 53 bits. So the next algorithm would be then range coding. That's a quite mathematical beast. It works by recursively embedding probability intervals of symbols. What does that mean? Every symbol has a probability to appear in the file. And the D has the biggest probability, as it is more often in the file, obviously. So what you do is you sort your symbols according to their probability, and build a table with the accumulative probabilities in this character string, which sums up to 1. Should be this way. What you do then, you go through your input stream, taking the D, which is in our table at position 0. So you take this part, the 0.29 part of the 0-1 interval, and embed the whole interval into this part. You embed into the 0.29 probability of the D. Yeah? The original interval has a length 1. This one only 0.29. And you go on. Then you take the R, embed an interval into the R's probability according to the cumulative and probability and the probability of the interval itself, it's the length of the interval actually. And so you go on. What you see here, the algorithm yields a number, a simple floating point number, which identifies the whole string. You just need to know the number and the probabilities of the symbols to decode the string afterwards. You see the resulting value will be around 0.91, which in our first step denotes a D. 0. is smaller than 0.29. 0.19 is smaller than 0.29, so we get a D. After that, we'll get an R, because the interval of the R falls over the value we calculated in the encoding step. Obviously, this algorithm too has very low memory requirements, and it seems to be very simple. But if you have longer strings of symbols, you will soon reach the accuracy of the machine. If you imagine you only have 32 bits, if you have 255 symbols, which with equal probability, you will in each step need 8 additional bits in the floating point number, approximately. So this is a problem, but there are more sophisticated implementations of this technique. You can find them on the pages I told you earlier. Okay, now that you know about compression algorithms, or the basic compression algorithms, we can look at the data we want to compress. If you compress data, you will notice that it's always handy to group similar data together. What does that mean? If you imagine music data, you have controllers for different aspects of your sound. You have your note data. It's always handy to group the controller values for the single controllers together in separate data streams, which are close together. Why is this this way? And the data is very similar. Imagine maybe a MIDI stream of maybe a sine oscillator, yeah, that controls some value. If you interleave it with other data, no patterns will emerge. If you consider it singly, just on a byte basis, you will after one period of the sine oscillator, you will have patterns. So that's why it's important to group similar data together, because the data behaves the same. The probabilities will be connected in a way. In code, it helps to use only a few machine instructions. Why is that so? What we want to have in our code to have it better compressed is a low entropy. So what we have to do is create code that has only a few symbols. And that's why you have to use only a few, or you should use only a few machine instructions. Also, if you're familiar with assembler, the addressing modes count into that. Addressing modes are typically encoded on a bit basis, which some kind disturbs our compression algorithm because it works on a symbol basis, on byte basis. So if you use different registers or different addressing modes, it will not find matches if you use the same registers again, but in different addressing modes. So you should stick to one addressing mode optimally. Also, another important thing is to avoid offsets. Offsets are quite bad. On 32-bit machines, if they are bigger, they are always 4 bytes. And also, most machines encode offsets as relative values. If you consider a jump, there is not a jump to address 1000 maybe, but if the instruction resides on address 900 and it should jump to 1000, there will be encoded as 100. So the actual address gets added by the offset stored in the jump. If you jump to or call this address from different locations in your code, no patterns will emerge because the offset is always different. Okay. Delta encoding helps sometimes. If you imagine, again, MIDI data, and you have maybe a melody. Chords have a mathematical structure. For example, minor chords have a distance of 3 and 4 half notes. So if you play different chords in minor, the difference will always be 0, 3, 4. So if you delta encode the values, only the first note will have to be stored, and all the others following in the chord are always 3, 4 if you play minor, for example. Okay, some words about simplicity and reuse. The Fabros guys already told us about that. Simple code. Why simple code? Code only compresses 2 to 1, according to my experience, and usually even less. Data, on the other hand, can be laid out for optimal compression performance. You have complete freedom how to arrange your data. So obviously data-driven architectures usually perform better than just coding everything. And if you go a step further, a virtual machine is a good choice for an intro system, for example. Because the code in a virtual machine actually is only data. And you can code, you can encode your actual code, your virtual machine bytecode, as you like. For example, you can eliminate the necessity for relative offsets for calls or something like that. Thus, providing the compressor with much more convenient data. You can find more matches if you use a pattern matcher, for example. Also, reuse of code is critical and quite easy, actually. The first thing that happens if you reuse code, you will have less code in your executable, obviously. This is good because code compresses badly, 2 to 1 or less. A good side effect of this is your routines will be tested more often, and you will have less errors in your executable afterwards. Also, the structure of graphics and sound is quite similar. Lots of the subroutines can be shared. For example, the interpolators. Consider, for example, if you want to control the brightness of your picture, that's just a spline describing some time-based change of brightness of your picture, which is basically the same as controlling the volume of a track in your music. So you don't have to code that twice. It's always the same. Okay, now we're getting to 20-4. What was the concept? Well, I've been doing 4K intros for a while now, and what disturbed me was always that the decompressors of common exa packers are quite big compared to the useful data that can be compressed then, which is left after the decompressor is stored in a file. So the main thing was the decompressor size should be as low as possible. My target OS operating system was Windows, so I wanted to optimize my executables. Windows uses the PE file format. I will explain it on the next slide, which has a certain structure which is quite redundant. You can leave a lot of things out, and you can even interleave information in the executable. The next thing was I wanted to use Microsoft cap compression because it's built into Windows. Most of you have probably seen already cabinet DLL in the system directory of Windows. And actually it turned out that the cap compressor is quite a capable one. It's quite a good one. The only thing was that its pattern matcher is not that good. But we come to that later. First, PE files. Well, what is a PE file? A PE file is image of a memory block which doesn't store the unused parts or parts where only uninitialized data resides. It has a directory which denotes the position of certain structures in the file. For example, imports. Imports would be like if you wanted to use some functions of Windows, you would have to tell the operating system in your executable that it should link the executable with the DLLs so you can call the functions actually. You have to know where they are. So you have to tell Windows that it tells you where the functions are actually. Okay, there are section headers. As I said before, the unused parts are left out of the file. The section headers describe the parts that are stored in the file. They say, is this part of the file executable? Is this writable or only readable? It also determines the location and size in memory, the location and the size in the file, and the protection information. As I said, is it readable, writable, executable, something. And after all those headers, there come the actual image pages that contain the data. A major drawback of the PE format in this case is, for my purpose, for coding for K-intros, was that the image pages must be aligned. There's in the headers there's an alignment field that accepts only certain values, must be a power of 2 and bigger than 512, if I remember correctly. And 512 bytes alignment is a lot, considering a 4K intro. So, what did I do? I optimized my PE file. I cleaned up the headers. In the headers there are stored a lot of information that are related to object files, which are not yet linked. That's difficult to explain. For you, it's important to know that there are a lot of fields which can be left blank, or so to speak, set to 0. But it's not always. It makes not always sense to set them to 0. Sometimes it's better if you copy values into those fields that reside before this field, so the compressor can find matches and encode it. Another thing was section realignment. The first thing I recognized when I looked at my executable files that were produced by Visual Studio was that Visual Studio created executable files with an alignment of 4 kilobytes, which makes sense because the page size of my system of PC is 4 kilobytes, but it doesn't make sense for my purpose. I rather let the executable load slower, but let it be smaller then. So what I did was I removed the trailing zeros, adjusted the alignment field of the headers, and even if there is initialized data in a section, you can cut the trailing zeros because the Windows Excel loader initializes the sections with zeros up to their virtual size. Then the next thing was it didn't make sense for me to have 10 or 12 section descriptors. It's a block of memory anyway, so what I did, I merged the sections so that I only had one section header left. This makes the file actually bigger because you have to inflate the differences between the sections again. You have to leave the space between the sections. Also, another drawback was that the protection suffers because if you only have one section header, this section always has to be readable, writable, and executable. You have no possibility of protecting your code, for example, from write access. But in the end, the file compresses better, and my goal was reached in a way. Another thing was the reorganization of imports. The imports are stored in a file in string form, which is quite big, as you might imagine. This technique is called import by name. Windows supports another import technique, which is import by number. It's less compatible because it depends on the operating system version. So Windows 98 will have different ordinals than maybe Windows XP. And so I came up with another technique, the so-called hashed import. It's just a name made up by me. What I do there is I create checksums of of the import names and only store the checksums and the algorithm to calculate them. Afterwards, if the file is loaded, I do the importing myself. I only store the DLL names, load the DLLs in, check their export table, and see which name fits my checksum, and then link it. So it's it's quite easy. And a lot of people almost killed me because I always linked by number. Mostly the organizers, because they had to cope with stressed intro coders trying to compress their intro on a party machine, because otherwise it wouldn't run. Okay, so cap files. As I said before, I wanted to use the cap compression of Windows, and the first thing that came up to me then was why not use the already given format that Windows has built in a way, which are cap files. Cap provides some compression mechanisms. The both that are implemented at the moment are MSZip and LZX. MSZip had quite a bad performance on small files, so I do not use it. LZX, on the other hand, is better than APEC or UPX on small files. The gain in size is around 500 to 800 bytes in a 4K intro, which is quite a lot. In using my intro system, it is an equivalent of an effect or two scenes. And the LZX compressor actually is pattern matching. It does a lazy matching, meaning it does not encode all matches. It tries to choose good ones. And while Microsoft has a very special opinion about what are good matches, and it's far from perfect. But if you know how it works, you can organize your data in a way so the matcher will find the matches you want him to find. Yeah, the matches are encoded afterwards using Huffman encoding. As I said before, if you use a simple encoding scheme on pattern matching, the performance isn't good, so Microsoft chose to use Huffman encoding for the matches. The decompression itself is a funny thing. Cap files can be decompressed using a batch file. Windows includes a tool, the extract32 executable, which can be used to extract the file and execute it afterwards. I show you in detail how this is done afterwards. The tricky thing was to let the command line processor ignore the binary data which belongs to the cap file. So I had to somehow prepend the batch to the compressed data, and the only solution I saw was to put the decompression code, the batch file, into the name field of the file that resides in the cap file. The other thing was an exe file decompressor, standard PE, more or less standard PE file. At least it loads and executes. That's all that counts. It uses the functions from cabinet DLL. There I use the interleaved headers technique again. You see that in detail in a moment. And there I use the trick I found together with Brück from Farbrausch. The headers of a PE file are executable, but they are not writable. That's an important thing to keep in mind. So what I did is, in this decompressor, I put the decompression code in the gap between the headers and the first section, which must be aligned, and there was enough space to put the whole decompressor into the header. Okay. So how does the batch file look? This is a clean version of the batch file that decompresses and executes my file. I use a temporary variable. It's a bit smaller in this way. An important thing to know is extract 32 hangs if the file already exists, so always delete it before you extract something. It's unlikely that in a temp directory resides an x.exe, which is important to the user, so we can safely delete it. After that, the batch file is extracted. It's a cap file actually with a batch in the file name field. So %0 is the name of the file which was executed, or batch file, and it's extracted to the temp directory x.exe. Then x.exe is executed and deleted afterwards. And then this exit is also a bit of a hack. When I put, as I already said, I put the batch file in the name field. Now the problem was if everything was done, there was the garbage for the command line processor, the binary data, the actual compressed data. So I had to tell the command line processor to exit before he sees it, and that's why the exit is there. It's actually the biggest version of the batch file. I think the smallest version I received was around 28 bytes. So that's the whole decompressor then. Okay, now the PE-exe decompressor. If you like, you can skip through the code. Would you like me to show the code? Yeah? You want to see it? Okay, so let's have a look. Ah, verdammt. So, well, it's NASM code, pretty much a standard assembler. As you can see here, I defined all the PE structures by hand. You can see the DOS header here, which normally is 32 bytes long, but in my case only 12 bytes. A neat thing about the Windows Exe loader is that it doesn't check the DOS header for correctness. It only looks whether there is the MZ at the beginning of the file. All other fields are ignored if there is a correct PE somewhere in the file. Well, the tricky thing about this is that at position 48, I think, in the file, there resides an offset which tells, and this belongs to the DOS header, which tells the Exe loader where to find the PE header. So the actual offset to the PE header resides here. So this whole part, and this is what I call header interleave. The MZ header and the PE header are interleaved here. Well, one bad thing is that my base of data will be at 0C hex, okay, which is not actually that bad. Yeah, that's the header interleave. Some more structures. Another important thing to know is the directory has normally 16 entries. In Windows XP, you only need to store 3, which has a neat side effect that you cannot debug the file anymore. Any debugger crashes if I load such a file. I put here 5 because Windows 98 and Windows 95 can't load files with only 3 directory entries. They need to have 5. Don't know why. Okay. Well, then there come my section headers. All bits are set, meaning my code is readable, writable, executable, discardable, movable, whatever. Then you also can see the offsets. The offset into the file, the size in the file, the offset into the file, the virtual size, which is 4 megabytes in this case, and the virtual address. The first section needs to be aligned. on a page boundary on the system, so this is 4096. Lower values won't work with Windows. Then there comes the code. We're still in the header, by the way. It's quite a long story. And here, the actual section starts. Here comes my actual data of the section. I didn't describe everything above, but the Windows Excel loader is quite a good pal and lets me execute the code anyway. Bad side effect of this trick is that every virus scanner will tell you that this file is ambiguous. Very, very ambiguous. Bad file. Okay, so here come the imports. You could do them by name too, but I decided against it because I import my functions from CRT-DLL, and to my knowledge, the ordinals in this file haven't changed since Windows 95. The functions in cabinet DLL are exported by number only. Microsoft's import library imports them by number by default, so I did it too. Thus saving another couple of precious bytes. Okay. Next thing was the intro system. Doing the compressor itself didn't make that much sense because with compressors today are that good that an improvement in compression wouldn't be possible in a big amount. Only a few bytes could be gained by creating a better compression algorithm. So what I decided to do was to use a virtual machine, as told before. I wanted some neat features also in the intro system: an object generator, the supershape object generator. I will show it afterwards. OpenGL texture generator, a modular softsynth, actually using OpenGL2, which brings me back to reuse. Modern machines or modern graphics cards have so-called float textures, and sound streams are basically floats. And our graphics card is basically a signal processor. So why not generate a sound on a graphics card? And that's what I did. The interesting thing was, which didn't come to my mind in the first place, that I would have as many tracks in parallel as I liked. Use two-dimensional float texture, and you're done. You have 256 tracks with 256 samples, maybe. No problem. Also a cool feature of that is that you know how mixing works. You just add stuff together. You want to adjust volumes, which is just the brightness regarding the graphics card, as I told before. And adding together is just drawing lines, textured lines with moving texture coordinate, and always on the same spot with blend mode to add. So you're done with mixing this way. We see the softsynth later on. Then, of course, I wanted to have a scripting engines. Scripting, everyone does it, everyone knows it's good, so I wanted to have it too. And now comes the neat thing about the script system. Scripting itself is quite a painful thing. Probably you scripted some things by hand already, and that's not the thing to do. You want to do that. So there should be tools for ease of scripting. But the drawback of tools is that you do not have full control about the flow of instructions. You cannot shuffle them around and leave instructions out that are redundant. So that's why I created the script compiler, which was basically the biggest effort in the creation of the whole system. We come to that in detail later on. So the virtual machine, what does it do? Well, actually, it's yeah, a machine that has 4096 registers. They can be treated as float or int, so no unsigned operations are possible in the machine. It uses separate code and data streams, as I said before, group similar data together, and it helps a lot. The instruction itself work on register ranges, and only the base register needs to be specified, and you need only 12 bits for it. That's 4096 registers. Okay. What kind of instructions do I have? I can specify geometry, materials, lighting, and camera setup. And that's already enough to generate textures and to generate sound. You do not need more. Consider, for example, a sawtooth. What is that? It's a line which starts in bright white and ends in black. That's a sawtooth. Quite easy to establish using the graphics card. So these simple instructions deliver everything to create textures and sound. The geometry is another thing. That is some more specific code. Maybe sometime I will do that using OpenGL2, but we'll see. Yeah, there are interpolators and oscillators. They are used to do all the scripting. I didn't want to have an event-based scripting engine because events become unhandy if it comes to compactness. A formula is compact. So basically what I do is I create a formula describing the whole behavior of the intro. And there are data movement instructions which basically connect these simple machines or the instructions between each other. Okay, the scripting engine. I use an XML format because I was too lazy to write an easy and reliable parser. That was the main reason. On the other hand, it's flexible and easily extendable, and versioning is no problem, which was quite an issue to me because my pals worked with the system already, and I made changes to the system every day, and I needed to be able to use their data files anyway afterwards. Well, the scripting itself, the scripts, as already said, are generated by tools. Scripting by hand should be possible because I wanted to do reordering and optimizing. Interpolation instructions. Oh, I'm getting redundant here. And the oscillators can be used too in scripting. Let's skip that. So this is an example script. What we see here is a screenshot of my latest 4K intro, which I'm still working on. What you see here is the script. You see, this is a so-called Schnecke. What is done is simply I made a keyword, and this has a lot of parameters. And as you can easily imagine, it's quite awful to edit an intro this way. So this is where the tools come into play. Okay, the script compiler. What does the script compiler do? Well, it's the XML script is translated into a byte stream. Yeah. What I wanted to do was that the byte stream is optimally arranged for the compressor, for the actual pattern matcher in the end. So what it does is it provides a pattern analysis. It checks the instructions for independence. Consider, for example, a tool generated code like enable lighting, does some stuff, enables lighting again, does some stuff, enables lighting again. So the redundant enables will be removed by the compiler. That's why also a data and state flow analysis was introduced into the compiler to be sure that not too much instructions will be thrown out. Also, the compiler does reordering of the script code. So I could have used another data format in the end because I'm not doing the reordering by hand anymore. The reordering is subject to the pattern analysis. So it's done in a way that the pattern matcher in the end will find a lot of matches and the code compresses good. Removal of unnecessary statements, as I already said. Yeah, the facts. Well, the compiler was a beast. You can say it this way. The intro system itself has about 470, I think, lines of code. There isn't more. The compiler itself has 15,000 lines of code. You might ask if it pays off, and it does. The original compression ratio, in my case, was about 4:1. And all my optimizations led to a compression ratio up to 10:1. And the actual stands are that the uncompressed data of the intro are 68 kilobytes in size, and they compress down to 3.5 kilobyte. Okay, now I want to show you my tools. It's the fun part. All the theory is gone now. Well, I decided to do my tools as plugins for standard software, so artists do not need to learn a new interface. Artists are always quite reserved when it comes to new interfaces. And also, it turned out to be difficult for the artist to choose a specific tool. One artist wants to use this tool, another artist wants to use another tool. And doing plugins lets you easily give them what they need. The interface is not that different between the tools, so you can easily adapt your tools into another program. A big problem for me was that most of the standard software didn't provide me with enough functionality GUI-wise. So at some places I decided to create a sub-interface which can be clearly recognized as my as my tool. But this was a thing which I couldn't avoid. The modeling for the intro is done using Cinema 4D object plugins. I'm working on Lightwave plugins at the moment. And I use the standard materials. The texture generator is embedded as a shader in these standard materials. And the sound is a custom software synth. So has its own interface. You can use any MIDI sequencer to control it. On the other hand, you can program, and I say program because it is this way, directly in the synth. You'll see what I mean afterwards. So let's have a look at the object generator. That's what it looks. Just standard Cinema 4D controls. So my graphians didn't have to learn anything new in this case. Verdammt. Also, the texture generator was embedded into Cinema as a shader, as you can see here. But I had to do a sub-interface to provide the generator with the necessary functionality that I wanted to have. Maybe have a look shortly. So it's working with the plugins is just like using Cinema 4D as you are used to it. So the object generator itself is based on a supershape formula, which basically is nothing more than an ellipsis of some kind. It's described in a more complicated way, and you can do almost any primitive with it. Yeah, magic. Ah, verdammt. So a cylinder is possible, or maybe it's my old data files for my own tool shared, not a different scaling. It's all the same, and also the what was a major improvement was that this was my first object generator, which was quite easy to control. You can do very, very complex scenes with it. For example, for example, this one. This is a short video of the actual work which I do for the 4K intro. As you can see, everything is modeled using those supershape objects, the plants as well as the rocks, as well as anything. I also introduced some into my system some of those cinema operators. For example, almost all of the deformers, which is quite a powerful thing, and graphicians always like it if they can use such stuff. You already know it anyway. The Farbros guys told you all of that. I won't go into detail here, I think. So, then let's have a look at the synth. This, I already said that you somewhat have to program your sound here, and as you already see, it's very complex to do even a simple song. One thing about operator stacking here, I didn't choose that because I needed recursion. Recursion is needed for delays, reverbs. Yeah, okay, but
you have more inputs. That's why operator.
Yeah, and I can the main advantage of this system is that you can, for example, connect the range of an oscillator to maybe the mode of a voice. No problem. That's what is done here. I have a frequency and the volume, for example, for a sawtooth oscillator, and I use those same frequencies in a square, but I do not want to store them. So what do I do? I take the frequencies from the saw and copy them. It's quite easy. Okay. So and what does it sound like? The song is, this song is, I think about 470 bytes compressed, or 480. I don't know exactly. I would have to do. It's pre-calculating, by the way.
Where's the bar?
There's sound. Sounds strange. The connector is broken. Okay, let's stop it. If you want, you can come here afterwards and listen to the song. I wanted to say something about the sound system, the actual player. Well, if some of you studied the MSDN in more detail, you will have noticed that there is a play sound function, which accepts a wave file that resides in memory. So the only thing the actual player, which plays the sound, does is I pre-calculate the wave file memory, 40 megabytes or something, and then I call play sound, and it plays the wave file. That's about it. So I hope you have taken something with you to experiment with, and I hope you have fun experimenting and misusing and abusing things. So thank you for your interest.